Hi. Uh, Today we're looking at reaction time and thinking distance. It's kind of carrying on from what we were doing last time, where we were talking about cars and driving and how fast is a normal speed and those sort of things. We're going to explain methods of measuring reaction time. We'll talk about typical human reaction times, and we'll explain factors affecting the distance for vehicles to come to a rest. But let's start off nice and simply with some questions. We have some questions here. A snail is crawling at 5 millimeters per second. It travels 2 meters along a wall. How long does this take? I'm going to do some kind of pointers, help you out. Sorry. Oh no, it's too dark. I'm going to help you out with some pointers, see what you can work out. So, what do we know? We know speed. They are traveling at 5 millimeters per second. The distance is 2 meters. So let's remember the equation. Speed is distance over time. Can you change the subject? If you can change the subject, then it's going to be quite easy, because if you make time the subject, then you can do the question. So go on, make time the subject. Time is, what have you got? Give you another chance. It is distance over speed. Let's stick this in. The other thing is we've got to convert this to meters per second. Well, I suppose we could leave it as millimeters, because it's per second. Oh no, that's so 5 millimeters. 5 times 10 to the minus 3 meters per second. So 0.005 meters per second. So 2 meters divided by 0.005. 400 seconds. That's how long it takes for a snail to crawl 2 meters along a wall. There we go. Let's see if you can do the next one. Again, I'll help you out. A rocket powered by a solid fuel motor has enough fuel for a 25-second flight. T is 25 seconds. If the average speed of the rocket during the flight is 200 meters per second, speed is 200 meters per second. What is the maximum range? So we want to know distance. So remember, change the subject. Make so speed is equal to distance over time. So give you a moment. Change the subject. Make distance the main object of subject of that equation. So distance equals speed times time. So we have 200 meters per second times 25. 5,000 meters. 5 kilometers is not bad. Okay, here we have a different set of things. I'm going to do this SUVAT. I'm going to write down all the things we know, leaving gaps for the things we don't know. It says a car accelerates steadily from 15 meters per second. 15 meters per second is its U, its initial velocity, to 25 meters per second in 5 seconds. T is 5. What is the average speed of the car? Okay, well, you can use this equation, average velocity, to work out. So what is the average speed of the car? Use this equation. Boink. What is the acceleration of the car? Ah, we then need the second equation. V equals u plus at, or I can help you to change the subject. V minus u all over t is a. That will allow you to do part 1 and part 2. The next question. There we go. It's the whole lot. Let me just give it a second. Can you work out the average velocity and then work out the acceleration? So the average velocity was 15 plus 25, all divided by 2 is 20 meters per second. Have you managed to work out this one? Pause if you need a bit more time. Got it? So 25 minus 15 all over 5 2 meters per second squared. Nice. Actually, before we do that, let's jump across. Do this one. Reaction test. Let's see. You could do this. Just Google reaction test. I quite like this one. I tried a few different ones. This one's good because you get an average. So you click to start, it goes red, and when it turns green, you press the button. That was particularly slow because I was talking. Oh, maybe that was slower. Wow, shocking. Bit better. We're all getting faster. Mm. 2.939999, basically 0.3 seconds. Decent. What was I on this one? Wait for green. 2.93. Actually identical. 2.93. 2.93. The average is 2.15. Haha, that means I'm slow. Brilliant. So that's my reaction. The reaction time is the time it takes between seeing or hearing an event and starting to brake, or hearing a stopwatch. And the thinking distance is the distance a car travels whilst the driver reacts to a hazard. So reaction time, or thinking time, is basically how long it takes for your brain to go, oh, something's happening, let's do it. And you then have to... So in the last video, the last clip, it was basically... is it green? If it's green, it's green. Obviously that was dramatised. The green goes to my eyes. The signal travels through my optical nerve, my brain, spine, down to the arm, motor, press the button. So that whole time, from that going green to me pressing the button on that one, 2.79 seconds. 2.79 milliseconds. Okay, so your reaction time, do a few goes, have a few goes. Now the important thing is though, this is about if you're driving, your reactions are really important. You're driving a car that weighs 1,000 kilograms and the child steps out in front of you, you don't react in time, you may hit that child or adult or whomever. It would be dangerous. So reaction time is how long it takes your brain to recognize there's something in the road and then press the brakes or do something. The thinking distance is how far the car travels whilst your brain is reacting. So for when I was doing that test here, that 279 milliseconds, if that was like real, the reaction has to go from my eyes seeing this go green, and if I was turning off by pressing it with my foot, then the signal's having to go from my eyes, brain, spine, down to my foot, and I press. So for 0.3 of a second, 319 milliseconds, the car is still moving. And if the car's still moving, It's still driving. It's gonna get closer and closer to that child. So it's really important that, one, you're not going too fast, because if you're going really fast, you can go quite far in 0.3 of a second. And two, don't do things to slow your reaction down time. Have you written that down? If you haven't, pause and copy those two things down. Okay, excellent. Let us move to the next part. Things that affect the thinking distance, the reaction time thinking distance, is things that may have happened to your body or things that might be happening outside of your body. For example, if you drink alcohol. Alcohol is a depressant. So therefore, it slows your reactions down, meaning the time the signal takes to go from seeing the stimulus to the response is increased because of it's actually slows down within the body. Synapses and other things slow down. Alcohol slows things down. Drugs slow things down. And being tired slows all of these things down. So you are more likely to have a longer reaction time when you're under the influence of drugs, alcohol, or exhaustion. There could be other things that happen that could cause this. For example, if there are people in the car talking to you, distracting you, chatting, kids in the back fighting, a dog jumping up and down, all of those things are a big issue. Eating and drinking, if you're having a sandwich or a drink, or just listening to the radio, the sat nav. Probably the biggest one though is using a mobile phone. I'm looking out the window as we speak, and I see so many people using their phone as they drive. As they're driving, they're just staring at it. They're not even looking at the road. A child could step out and they wouldn't know. They'll just run them over because they're not even looking. That's not just distracted. That's completely insane. Let's look at an example. So, for a car travelling at 30 miles an hour, how far you would travel whilst you react? Let's do a really exaggerated. We're giving a reaction time of half a second, okay? So if you're travelling at 30 miles an hour, first of all, we've got to convert to meters per second. 30 divided by 2.2 equals 13.4 meters per second. So 30 miles an hour is equivalent 13.4 meters per second. Okay, and if you remember the equation, distance is equal to speed times time. So 13.4 times half a second equals 6.7 meters. In half a second, travelling at 30 miles an hour, a car will travel nearly 7 meters before you've even pressed the brake. That's quite a long distance. So, these are things you have to... Obviously, that's quite a long time. What did I record? Mine was 0.3. So, 13.4 times 0.3. 4 meters. If I was using my normal reaction time, it'd take... the car would go 4 meters. So yeah, thinking distance, small time, still quite a long distance. Do you have another one? Calculate the thinking distance for a car travelling at 50 miles an hour. Let's first of all convert 50 miles per hour. Is in meters per second. You do 50 divided by 2.2. Is 22.7. Now, why don't you use for the next part your own reaction time? So, if you've done a reaction time, if you're a fast reactor, mine was what was it? .293. So let's use that. So speed times time, so 22.7 times 0.293 equals again. 6.7 meters. So traveling at 50 miles an hour with my reaction times, the car travels 7 meters before I even hit the brakes. So if a child stepped out and they were 6 meters in front of you, I wouldn't have even tapped the brakes before the car hit them. Important. There's one more way to measure your reaction time, and you can do that at home. You can do this. We've done it in school before. You have a ruler. You need a person. You can't drop the ruler yourself. Do I have a ruler here? No, I don't have a ruler on me. You can't drop the ruler yourself because you know you're dropping it. You can just do. And that doesn't go anywhere. So you have to have somebody else to drop it. So you don't know when it's being dropped. So it's really testing your reactions. And you drop it from rest. And then what you do is you work out how far it's travelled. So this will be, if I caught it at say 15 centimetres, maybe you write 15 centimetres, which is the same to 0.15 metres. It's accelerating due to gravity, 10 metres per second. Its initial velocity, well, if you're dropping it from rest, that is actually 0. We can then work out its final velocity, and we can use that to work out how far it goes. Whoops. Oh, look, they've got the worked answer here. Forgot about that. God, this person's really slow. They caught it in 25 centimetres, 0.25 metres. That's like at the top of the ruler, like the whole thing passed. Acceleration due to gravity is 10. Their initial velocity is 0 meters per second because they drop it from rest. So basically you use this equation, b squared minus u squared equals 2as. U squared is 0, 2 is 2, a is 10, and s is 0.25. So v squared minus 0, so v squared equals 2 times 10 times 0.25. So v is the square root of 2 times 10 times 0.25, and that gives us a speed of 2.23 meters per second. Use speed and distance to estimate the time. Well, 0.25 divided by 2.23 equals 0.11. That's such a fast time. That's a rubbish method. Rubbish method. Don't bother with that one. But it's a good example. Okay, so just time. This is it. We are now at the end of this talking part where you have to just answer questions. 4 questions. Describe a link between reaction time and thinking distance. Calculate the reaction time of a driver in a car that's travelling at 50 miles an hour. The thinking distance is 20 metres. Suggest a reason for this reaction time. Obviously it's not going to be 0.2. Explain how you can use the dropping ruler experiments to show different reaction times. Okay, so what would it look like if you had people of different reaction times? And you stand at the finishing line of a 100-metre race on sports day. You press the start button when you hear the gun, and the stop button when you see the winner cross the line. Suggest and explain whether the accurate time is more or less or the same as the reading on the stopwatch. Okay, so pause. Answer those questions. I'll give you the answers next time. Okay? Bye.